Single displacement reactions. What characterizes this type of reaction is the fact that you start with an ionic substance and you combine it with an element in its most elemental form. What ends up happening is that one of the components of the ionic salt exchanges with the element. In this case, if we assume that A is the cationic portion of the ionic substance, then we're exchanging the cation with the species that used to be all by itself. And now the cation that we start with is the isolated species. So there is this exchange of one element for another in a single displacement reaction. And because of that, both the cation that you start with and the element that you start with will change charges as the reaction proceeds to the product side. On the other hand, the species that is not being exchanged, in this case the anion, will maintain the same charge. And just to keep this general, as long as element C is a metal or hydrogen, you will undergo this exchange of cation for element, okay? But it has to be metal or hydrogen as far as the identity of C. Okay, now a few things that I need to remind you of. When you're dealing with the elements in their elemental form, there's 11 elements that actually are present as gases at room temperature. Specifically, we have hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. There's a total of 2 elements that are present as liquids at room temperature, and the rest of the elements are all solids. That includes all of the metals with the exception of mercury and a good chunk of the non-metals. Okay. Now, one additional factor that needs to be mentioned is that when dealing with the elements in their elemental form, you have to recall your Hofbrinkel elements, your dihydrogen, your dinitrogen, your dioxygen, your difluorine, dichlorine, dibromine, and diiodine. Those particular elements are going to not only be most of them gases at room temperature, but they will also be diatomic. Okay, something to remember. All right, now, in terms of the exchange of the cationic component of an ionic salt with an element, there's something known as the activity series that can guide you in deciding whether a reaction will even take place in the first place. And this is a qualitative means for, predicting whether your single displacement reaction is likely to occur or not. So for instance, if you're mixing aluminum, elemental aluminum with iron 2 nitrate, you can look at the table and say, okay, well, aluminum, which is the lone species, the lone wolf, is in fact higher on the list than iron. Okay, and iron is a cationic component. Remember that because aluminum is a metal, we are going to be exchanging the cationic component of the ionic salt. Since aluminum is higher than iron, this tells us that this reaction will indeed happen. That's what the activity series says. The higher up on the table you are on the activity series, the more reactive the neutral metal is. And vice versa. The lower on the table the neutral element is, the less reactive it will tend to be. Okay, now, to determine the products, which is really the task that you're going to be in charge of performing, you have to keep in mind that the moment aluminum exchanges iron, it will now develop a charge. And for this, you will have to keep in mind what the charge of this, certain elements are, like groups 1, group 2, group 3, zinc, silver, cadmium, you have to remember those specific charges. Alright, so we get aluminum 3 plus since aluminum is in group 3. Now you bring the unit over, which is nitrate. So nitrate is brought over with a negative charge. And the iron is now going to be all by itself. That one now has no charge, is by itself. And because it's a metal, it's going to be a solid, right? So now you use the charges of aluminum and nitrate to come up with the proportions. The 3 goes in front of nitrate, the 1 goes in front of aluminum, and you end up with the following species that I'm writing as AQ for the time being. In a little bit, on a different lecture video, we're going to learn about how to predict if the ionic salt is soluble or not. Let me show you 2 more examples to finish this idea. And of course, before we get to that, we need to balance the reaction, right? So if you look at the nitrates, you notice that there is 2 nitrates on the reactant side, 3 nitrates on the product side. So use the even odd proportions to balance the nitrates, meaning that you multiply the iron by 3 and you multiply the aluminum nitrate by 2. Since you now have 3 irons, you have to multiply the iron here by 3. And since you have 2 aluminums now, you have to multiply the aluminum on the left side by 2. Okay. Now that's balanced. Let's do another example. If we have mercury 2 chloride reacting with hydrogen, we have the same idea. The element that is by itself and neutral is hydrogen. So we ask ourselves, is hydrogen higher on the list than mercury? And since hydrogen is a lone species, we are going to be exchanging the cation. But is it higher than mercury? If we look at the list, we realize that indeed hydrogen is higher than mercury. So this reaction will actually happen. And hydrogen, when it exchanges for a cation, has to develop a positive charge. Specifically, it has to develop a +1 charge. Chloride will still remain chloride, so it will have a -1 charge. Notice that I'm not bringing the subscript, just the unit, which is chloride. And mercury will now be all by itself. Alright, now use the charges to come up with the proportions. So there's 1 H for every 1 Cl, and that will be your AQ substance. Perfect. Now we have to balance the reaction, and notice that we have 2 hydrogens on the left side. We only have 1 on the right side, so we put a 2 in front of HCl. That gives us now 2 chlorines on the right side, 2 chlorines on the left side, 1 mercury on the left side, 1 mercury on the right side. The equation is balanced. Last one. If we react potassium with water, at first you might think that this is not exactly a single displacement reaction, but if you rewrite water to look this way, HOH, what you're going to realize is that, yeah, the first H can act as the cationic component of water. And in that case, we look at potassium and ask ourselves, is potassium higher than hydrogen on the table? And as you can see, that is indeed the case. Not only is it higher, but it's a lot higher than hydrogen, meaning that this reaction could potentially be explosive. Alright, now, what's going to happen is that when potassium replaces H, it will develop a charge. Its charge will be +1 since it's in group 1 of the periodic table. The hydroxide that you have left over will still remain there with its 1 minus charge. And hydrogen will now be by itself, but because it's by itself, it has to be diatomic and it has to be a gas. Alright, now use the charges of potassium and hydroxide to bring them together. And now let's balance the equation. We have 2 hydrogens here, so we probably want to place a 2 in front of water to balance the initial hydrogens. That gives us 2 hydroxides on the left side, so we need to add 2 hydroxides on the right side. And now we need to balance the potassiums with a 2, and now we have balanced the reaction.